In this short video, I'm going to talk about the RidleyWorks simulator. We get a lot of questions about this, and there's a lot of misunderstanding about our simulator. It runs so quickly that people assume that we're using either canned waveforms or we're doing some kind of average method of simulation or some kind of trick that they've heard about, but we're not actually doing that. We're doing real cycle-by-cycle simulation inside RidleyWorks. So let's go look at the opening page.
Click on Specifications to start your design.
Here we are with a forward converter. I've chosen that because it's got more interesting waveforms to look at. And the design of the output of this is a 12 volt 20 amp converter running at 100 kilohertz. And if we go look at the input current here, we can see now just a continuum of waveform here because the resolution of the screen can't show all the cycles that we've got. So let's zoom in a little bit here by turning the time-based dial. And now you can see the individual cycles of startup. So here it goes maximum duty cycle, then a minimum. That's almost like a subharmonic oscillation on the way up. Then it goes through a maximum duty cycle, another one, and then a small pulse and narrow. And now in this region here, the converter is actually current limiting. Why is it important to simulate current limiting? Well, if you're designing things like magnetics and inductors, that's where you got to design the magnetics. It must not fail during startup. So you could check your converter during startup, and you've got to see the current limit. Make sure you've got that set properly to operate without saturating the magnetics. Now in here you can see on each cycle we're simulating the on time, we're finding the convergence to the switching point. We have a very special algorithm for finding that point. And then if there's discontinuous mode, it will detect that as well. But the simulation is indeed cycle by cycle. It's exactly what you're going to get out of LT Spice if you run it in there, only it's going to run a couple of orders of magnitude slower. And we'll do a demonstration later on of how we build that link as well. Now, I mentioned earlier, we do not use average models here. So people say, well, how can you be doing this? Is this done with a piece of code on the side? Is there some kind of built-in simulation package that's trying to do this? It's no, it's built straight into the worksheet. So here is our simulation page. And you can see here just row after row of calculations of numbers. These are just straight down calculations. It includes the controller, the power stage, current limiting, quasi-resonant mode. If you have that for flybacks, there's so much built into this page. And it's very elegant and a very fast simulator that nobody else has really even tried to match it. If you look at other designers out there, they might show you one cycle or two cycles, but they're just drawing a picture on your screen. We're not doing that. And this page here, it goes at least 36 rows across, and it goes 8,000 rows down before you reach the end of the data set. And that's how we get our, 4,000 rows down. That's how we get our 800 data points for simulation. So it's a very powerful simulator. It lets you do things. The whole point is to simulate so quickly you can design while looking at waveforms. And that's the whole point. You want to break away from equations. You want to be visual, just like being on the bench, so you can feel the circuit. Let's look at our output voltage here. Let's hit continue. And you see the speed of the simulation. And now let's dial that down and get some more waveforms in here. And let's put a step load on this. So we're going to step the load from 100% down to, let's say, 70%. Okay. And now let's go to our minimum so we can see all of this. And there you can see our transients happening. So here the converter is stepping down to 70%. Here it's stepping up to 100%. And you can see it's an asymmetrical waveform. You couldn't do this with small signal because it would give you the same result. But in one side you get current limiting, the other side you don't get current limiting. But you do get overshoot of the inductor energy. So if I hit continue again, you can see the first pulse undershooting. And now when you zoom in on that by turning the time base, you can see all the characteristics of that output voltage overshoot. So there's a time constant associated to the converter responding, another time constant associated with it settling. This little bit of ringing here will be related to the phase margin of the system. And later on we'll see in RidleyWorks how we can actually adjust the control of the system and watch the simulation of the converter going at the same time. So on this we could actually change the capacitor. If I want more capacitance on the system, we see how the overshoot changes. There. So we've changed the overshoot by increasing the capacitance on the system. Every time I click on this capacitor and change it, I redesign the loop. So I'm getting the optimal response. This helps me choose my capacitor correctly. You know, not just with some vague equation, but we're looking at large signal simulations when we do. So this is the power of the built-in simulator. Now, we're not trying to be something like LT-Spice. This is not a general purpose simulator. This is just for PWM converters only. They have very special characteristics in the power stage, and they have very special characteristics in the controller. But even so, it's still a fifth order system that we're trying to simulate here. And we've had this simulation algorithm in place for well over 20 years now. And as I say, nobody else has been able to reproduce what we're doing here, because it is pretty remarkable. So I hope you enjoyed it. I hope it gives you a little bit of insight. And, you know, get yourself a copy of RidleyWorks and enjoy using our simulator and design in a way that you never thought was possible. Thank you.